What's up, guys? Welcome back to day four, I think, of programming every day until I'm employed. Um, I actually started this problem, but I forgot to record. So, um, this is what I have so far. Mm, I have like the result variable, left pointer, a previous to keep track of like the character we just saw. Oh, and the aim of this problem is to choose any character of the string to change to the uppercase, um, in the longest repeating character replacement string, right? So I have this loop that iterates throughout for the right pointer, and then it checks if the previous is not none and it's not equal to what we just saw, like the current one, and k is greater than 1, we decrement k, and then this one checks if k is less than or equal to 0, and we update the max result, and then update the left pointer, and then update the previous character. Um, so I'm passing these regular test cases, but I'm not passing like every single one. I only have 19 out of 49 correct. So, um, to be honest, I don't know what's wrong. I've been thinking about it for a bit, so I think I'm just gonna watch the solution after I try maybe like 2 more minutes. But yeah. Um, hmm. See why I'm failing this one. Oh, is it because I'm not including the new character? Wait, no. Because here XX3, but I put 4, which. K equals 0. Okay. Okay, I think I'm just gonna watch the solution.
Hey everyone, welcome back, and let's write some more neat code today. So today we're going to solve longest repeating character replacement. And so this is another problem from that blind 75 list. So we're going to be one step closer to completing the entire list. The link will be in the description to this spreadsheet if you do want to take a look. And hello to the 6 people that are currently viewing the spreadsheet right now. You're going to be in the next video.
看你的 essay, you
I
wrote
know.
it 6 years old.
Yeah, I know.
Pretty good.
But okay, so let's get into this problem because it's another pretty fundamental problem that's really good to understand. So we're given a string s and a single integer k, and so basically they tell us that we can choose any of the characters in the string and change it to any other uppercase English character. So in this problem, every character in the input string is going to be limited to uppercase English characters, and we know that there's 26 uppercase English characters from capital A to capital Z. And so basically we can perform a replacement on any of the characters at most k times. So we're allowed to replace k different characters in the string to any other character we want. And what we want to do is return the length of the longest substring containing the exact same character we can get after performing at most k different replacements. So we just want to return that length. We don't actually have to make those replacements in the input string. So in this case, when we take a look at the input string, we have AB, and we're allowed to replace 2 of the characters. So what's the longest substring we could get with the exact same character? Well, we could replace one of the B's. We could basically replace both of the B's with a capital A, and then we get 4 A's in a row, which would give us an output of 4. And we could technically also do the opposite. We could replace the A's with capital B's, and that would give us the exact same result, a length of 4. So I'm going to show you how you can solve this problem in big O of n time, and technically it's going to be big O of 26 multiplied by n, which we know is also reduces to big O of n, but there's actually technically an easier way to do it, or at least a more simple way to do it, which is just going to be a flat big O of n. We don't even need this 26 constant.
开着温的把那个扣子也放进来。
No, close the door.
你看他房间 so cold, he opened the window.
Bro, I don't want it. I don't like
你
it
们两个
cold.
project 一个要 cold 一个要 hard 这怎么办啊？
No.
But this way is actually pretty tricky to get to, so I'll be going over a little bit of it, but this is kind of the main way that you'd want to solve this problem. So let's say we're given an input string like this, and we're given a k value. Now, the most brute force way would just be check every single substring, right? And if we were checking every single substring in the entire input array, we know there's n squared substrings, so that wouldn't be the most efficient way to do it. But even if we were doing it like that, what exactly are we looking for? If we're looking at a particular substring, how do we know if this substring is valid? Because remember, at the end of the day, we want to maximize the result, right? The result is going to be the longest substring that contains a single character, and we can make 2 replacements. So let's look at this substring alone. How do we know if it's valid? Well, which character are we going to replace? Are we going to want to replace the B's in order to make it all be to match A, or would we want to replace the A in order to match it with the rest of the B's? Of course, we're going to replace the character that occurs less frequently, right? Because the number of replacements we have is limited, so we would want to replace the characters that are less frequent. So in other words, we want all characters in a particular window to match the most common character in that window. So what we're going to be doing is we are going to have a hash map or a array, which is going to take every single character. In this case, we only have characters A and B, and we're going to count the number of occurrences of each character. So for example, if we were looking at this substring, we see that there's 3 B's and we have a single A. So how do we know if this window is valid? What we're going to do is we're going to take the length of the window, which is going to be 4, right? We're going to take the length of the window, right, which we know in this case is 4, and we're going to take the length or the count of the most frequent character. In this case, we know that that's B, and the count of it happens to be 3, so we're going to take 4 minus 3, and from that, we're going to get a 1. Now, what does this value 1 tell us? It tells us the number of characters in our window right now that we need to replace in order to make it match the most frequent character B, right? We have a B here. We want everything to match a B. In this case, we only have an A, right? But it could be possible, like, who knows, maybe that we would have a C over here, right? Or an X over here. And it doesn't really matter what the characters are. We just know that B is the most frequent character in the window, and the other characters that are not B, A and Z, for example, are the characters we want to replace. So we can calculate the number of characters we want to replace just like this. And so we want to replace one character. How do we know if we have enough replacements to do one character? Well, of course, that's our input parameter k, right? So what we're confirming here is that this value is less than or equal to k. As long as this condition is true, that means our current window is valid. That means we have enough replacements to make those replacements in our current window. So this is the main condition that we're going to be checking. The other question is, how are we going to know which character is the most frequent? Well, the brute force way is going to be taking a look at our map of counts, and we know that the max size of this could possibly be 26 because we'd only have 26 different characters. So finding the max character is going to be big O of 26. So that's a little bit more inefficient than we would like, but it's technically still linear time. Like the overall algorithm is still going to be linear time. The last thing that we're going to have to do though is to this equation, we're going to have to add a sliding window technique. So basically what we're going to do is we're going to take our window, start at the beginning, expand it as much as we can as long as the condition that we mentioned is valid. If the condition is not valid, then we're going to take our left pointer and then shift it as well until the string becomes valid once again. So we're going to have a left and right pointer. So initially left is going to be at the beginning and right is also going to be at the beginning. And also the counts of A and B are initially going to be 0. Now we're going to look at the first character, right? That's where our right pointer happens to be. We're going to look at it. We're going to say, okay, we have a single A, right? We're going to take our count of A and set it to 1 now. So is this window valid? As in, can this window be the exact same character within 2 replacements? Of course it can, right? That's kind of the trivial case, but we would still calculate it. And the way we would calculate it is get the size of our window. Right now we can see the size of our window is 1, subtracted by the count of the most frequent character. In this case, we know the most frequent character is A, 1 minus 1. Is that less than or equal to K? We know K is 2, so of course this is going to equal 0. 0 is less than or equal to 2, which is K, right? So of course this window is valid. That's kind of a trivial case. Next, we're going to shift our right pointer to the next character, right? So now we have a B, so we're going to increment the count of B in our map. So B is now going to be set to 1. In this case, the length of our window is 2. The most frequent character is either of these, right? And the count of that frequent character is going to be 1. So we're going to get 2 minus 1 equal to 1. So this is the number of replacements that we would have to do. And looking at our current window, that makes sense, right? We'd have to replace at least one of these 2 characters. So we're going to ensure that the number of replacements that we need to do is less than or equal to K, which is 2. Of course, that's true. So our window is currently valid. I guess I did forget to update our result. So since this window is valid, the length of the window is going to be set to the result, right? So right now the result is 2. 2 is the length of the longest window that we can get. So that's our result for now. So now let's continue. Next, we're going to shift our right pointer to the ensure that the number of replacements that we need to do is less than or equal to K, which is 2. Of course, that's true. So our window is currently valid. I guess I did forget to update our result. So since this window is valid, the length of the window is going to be set to the result, right? So right now the result is 2. 2 is the length of the longest window that we can get. So that's our result for now. So now let's continue. Next, we're going to shift our right pointer to the third character. So now we get another A. So we're going to take the count of A and increment it all the way to 2. And we're basically going to repeat our algorithm. So once again, we're going to get the length of the window 3 minus the count of the most frequent character. We see the most frequent character is A. So the count of it is 2. 3 minus 2 is 1. Is that less than or equal to 2, which is K? Yes, of course it is. So this window is also valid. We can update our result now to 3. So we found another window even longer. So I'm going to take our right pointer once again and then shift it over to the B. So now we're going to be, since we reached another B, we're going to increment the count of B to 2 now. And so the length of our window now is 4, and the count of the most frequent character is either of these, and that's going to be 2. 4 minus 2 is equal to 2. Is that less than or equal to K? K is 2 in this case. So of course, once again, this condition does hold. So once again, we found a window that's longer than our result. We found a window now of length 4. And so once again, we're going to take our right pointer and shift it. So now another B, let's increment the count of B to 3. So the length of the window now is 5 minus the count of the most frequent character. That character is B. 5 minus 3 is this 2, and less than or equal to K. Of course, it's still true because when you look at our window, we have 3 Bs. So that means we're going to be replacing the A's. So we're going to need to make 2 replacements, and we are allowed to make 2 replacements. Okay, so now we're finally going to get to the case that I mentioned earlier where we're going to have to take our left pointer and then slide it to the right, which is why this is a sliding window problem. So now we reached an A. So we're going to take the count of A and set it to 3. So now we have A count 3 and B count 3. So let's take the size of our window, 6, subtract from it the count of the most frequent character. It's going to be either of these, so 6 minus 3 means we need to make 3 replacements. Is that less than or equal to K? K is 2. So we exceeded K, right? We exceeded the number of replacements we're allowed to make. If we wanted this window to be valid, we have to replace 3 characters in it, but we're not allowed to do that. So what we have to do is shrink the size of our window until we are valid. So we're going to take our left pointer and shift it to the right. So now the left pointer is going to be over here. It's going to be at the B. So since we removed this A from our window, we have to decrement the count of A in our window. So I'm going to cross this 3 out, and now it's actually going to be set to 2. I kind of ran out of room, but I hope this is still readable. So now the count of A is 2. So now let's once again check, is our window valid? Well, the size of the window now is 5, and the count of the most frequent character is B, and that's going to be 3. So 5 minus 3 is going to be equal to 2. Is that less than or equal to K? Yes, we are once again valid. So this is technically a valid window, and I think I forgot to update the result earlier when we had a window of size 5. So the result right now would be size 5 because the longest window we can make is either this window or the window that we had earlier with these first 5 characters. But yeah, and so at this point we would stop our algorithm because we did find a window of 5 that is valid, and our right pointer cannot be shifted anymore. So this is the general algorithm. So it's a basic it's a fundamental sliding window problem with this particular condition being important. But there's actually one way you can do it without having to look through the entire hash map every time you want to find the most frequent character that occurs. And it's kind of tricky to arrive at the solution, but it's pretty easy to implement once you can figure it out. I'll explain the algorithm at a high level. I don't want to waste too much time on it, but basically we're going to be having another variable, and it's going to be called max frequency, basically the count of the most frequent character at any given time. So basically, for example, if we had A as a count of 3 and B as count 2, we'd say, okay, the count of the most frequent character occurs 3 times, so max F is going to be 3. And so anytime, if we got a B, let's say we incremented our B all the way up to 4, then we'd want to update our max frequency to 4, right? So we'd always want this to be the most frequent character. Now, the one problem is, if we're trying to maintain the count of the most frequent character, what happens when we take our left pointer, for example, right, and then shift it, right? When we do that, we're basically removing a character, and therefore we're going to have to update our count map, right? We are going to do that, and if that does happen, right, let's say we took B, and then from 4, we decremented it all the way down to 2, for example. Then we'd have to rescan this entire map and then find, okay, what's the new most frequent character, right? So we'd have to take our max frequency and from 4 downgrade it all the way to a count 2. We'd say, okay, the count of the most frequent.
So I'm just reading this article thing real quick.
character occurs 3 times, so max f is going to be 3. And so anytime, if we got a b, let's say we incremented our b all the way up to 4, then we'd want to update our max frequency to 4, right? So we'd always want this to be the most frequent character. Now, the one problem is if we're trying to maintain the count of the most frequent character, what happens when we take our left pointer, for example, right, and then shift it, right? When we do that, we're basically removing a character, and therefore we're going to have to update our count map, right? We are going to do that, and if that does happen, right, let's say we took b, and then from 4, we decremented it all the way down to 2, for example. Then we'd have to rescan this entire map and then find, okay, what's the new most frequent character, right? So we'd have to take our max frequency and from 4 downgrade it all the way to a 3, for example. So then we'd have to set it to a 3, and that would basically defeat the purpose, right? We'd still have to do that big O of 26 calculation to scan through this, but it's technically true that you don't have to decrement this max frequency. But the main idea is this. The result is only going to be maximized as we find a new max frequency, right? Because remember what we were doing. We were taking the length of the window subtracted by the max frequency, right? Whatever the most occurring character was, and we wanted to minimize this, right? So basically we want the length to be maximized because that's what our result is going to be set to. So therefore, we also want the max frequency to be maximized because we want to ensure that this is less than or equal to k, and k is going to be a constant. So for example, let's say I had a max frequency of 4, but let's say now the new max frequency got downgraded to a 3. I'm still going to leave this as a 4 because it's not going to change our result. Because for example, if I had a 6 minus 4, that was less than or equal to k, which is 2 in our example. And if I leave this as a 4, I'm basically overestimating what the max frequency is. But we know at least at one given point in time it was a 4, so therefore we were able to take the length 6 and then set it equal to our result. And now, so let's say our result is now 6. If we're ever going to increase the result from 6 to another number, like for example 7, we would require our max frequency to increase. If it stays the same or if it decreases, our result is never going to change because we only change our result when we increase our max frequency, because that's the only way this condition here is going to be true. So if our max frequency is downgraded, we don't have to actually update it. We don't have to look through the entire hash map to find the new max frequency. But if we increase our max frequency, for example, if I took this A and then from 3 I set it equal to a 5, then that's something we can check in big O of 1 time, and then if we increase this, then we definitely do want to update our max frequency and increase it, and that's something we can do in big O of 1 time. So I know I probably went a little too long into this, but the main idea here I'm trying to get at is the easy way to solve this problem with a sliding window is going to be big O of 26 times n, which is technically linear, but there is a clever way to do this in big O of n time that honestly I didn't figure out on my own, and I wouldn't really expect other people to be able to figure it out on their own, like in an interview at all. But I will show the standard solution, and I'll also show the code for this more optimized solution. Okay, so now let's jump into the code, and the code is actually a lot easier than the visual example that I gave, a lot shorter for sure. So we're going to have a hash map to count the occurrences of each character, and we're also going to have a result, which is going to tell us the longest substring that we can create with k replacements, and we're going to have a left pointer, which is going to be at 0, and then our right pointer is going to go through every single position in the entire string s. So what we're going to do is for the character at position r, we're going to increment the count of it. We're going to take 1 plus whatever the pointer, which is going to be at 0, and then our right pointer is going to go is for the character at position r. We're going to increment the count of it. We're going to take 1 plus whatever the count currently was, count.get this character, and if the character doesn't exist in our hash map, we're just going to return a default value of 0. That's what this function is doing. And so before, what we're going to obviously do is update our result, right? And we want to set the result equal to the max that it's ever been, and set it basically equal to the size of the window. We can get the size of the window, so we're going to take the max of result and the size of the window. The size of the window can be gotten with right minus left plus 1. But before we do this, before we update the result, we want to make sure that the current window is valid. So what I'm going to do is basically say while, and I don't think you would actually need a while here. You could just do if, but I'm just going to do while just because. So while the window is not valid, and we would know that by taking the length of the window, which we have down here, so I'm just going to copy and paste that, the length of the window, subtracted by the count of the most frequent character, which can be gotten with max of count.values. Right, we're basically going through the hash map, which could be size 26, and just getting the max value from it. So this is the number of replacements that we have to do, and if the number of replacements was greater than the number of replacements that's allowed, which is equal to k, that's when we would want to shift our left pointer. So we'd want to increment our left pointer. But before we increment the left pointer, we'd want to take the count of the character at the left position and then decrement it by 1. And that is the entire algorithm. After all of that is done, after we've gone through the entire string, then we can just simply return our result. And as you can see...
Dang. I think this is definitely the hardest problem I've done so far. I don't think my code was accounting for the fact that there could be different variables or like different characters. To have a hash map, sliding window. So all the number of flips is while the number of flips is that you need is greater than k, we move left up. Otherwise, we take the max of the current window in itself. Okay. Like, I get it while he was explaining it, but I just don't think I'd be able to come up with that on my own. So, you have a hash map. Set up left and result. And then for R in. So that's increasing the count. So while the length of the window minus the max of the hash map is greater than k, we want to shrink the window. Okay, then we want to remove it, shrink the window. Otherwise, increase the new length. What'd I do? Wait, what? What did I do? Probably a stupid mistake again. Oh, the left. Okay. To be honest, I'm not gonna watch the more optimized one because, I mean, like you said, they wouldn't be able to figure out in a real thing. Bro, what?
Nothing. Just came to bother you, but you're on the phone.
And then, alright, so we have a hash map. We have a. So the number of flips is the max number in the current sliding window. Minus. Okay, so the current window minus the max number of values. So if that, okay, so that's not satisfied, you have to increase it. We have like a rolling hash to keep track of it. Okay, that makes sense. Like, I definitely need to review this more though, so I'll probably come back to it. I'll put that in my spreadsheet. Fuck. What did I say before? Yeah, I think that's a good explanation. But I'm gonna say use rolling hash. See, this one is a 1 day, so it was probably very hard. Let's see. Should I keep a physical journal of notes? Probably be easier, right? Like a page for every problem. I don't know. Okay. I think I definitely need more practice for sliding window. If S2 condenser. Do you have to sort this? I'm thinking sort. I don't think that'd be very efficient though. How many times have I attempted this? Okay. This was all on the same day. August 1st. It's been how many months? It's been a while. Given two strings. Okay, so I'm how some edge cases like if length of S2 is less than then we can return false because automatically you can't have a substring. So we sort it to get in the same order, right? And then I think this would be a static sliding window. Is that what they call it? So left equals 0. Let's set right equal to set R equal to length of S1. No, I don't. I think this would be n squared. N squared log n. This definitely is not efficient. How do you do a sliding window of this? Maybe a set? This is like pattern matching. But the ones we learned were you always had to check a good amount for each of these. Would that be n squared? Brute force. Maybe we check it one and then every time we roll it over. I feel like I'm on the right track, but how can we optimize the sliding window? How do you splice again? Okay, so you can't sort a string. There has to be an indirect way. Okay. Oh no, you can't sort it. Oh, it's not help me. Oh wow, I actually got a good amount. That is true. They have to be consecutive, so you can't sort. Dang, I have no idea how to do this then. I low-key have no clue. I think I'm just gonna go ahead and watch the thing for this one.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem permutation in a string. And there's actually two solutions to this problem. One is the 26 times n solution, and there's another solution that's actually just big O of n. Now we know that a constant number here doesn't actually affect the overall time complexity, but that being said, I'm still going to focus on the slightly more optimal solution because it's a little bit more difficult, but it's also interesting, and it's a pattern that's actually used in other LeetCode problems as well. So we're given two strings, s1 and s2, and all we want to do is return true if the string s2 contains a permutation of S1, and we return false if that's not the case. Now, you can get bogged down and really confused with the explanation of Ku2 as warranting set solution, and there's another solution that's actually just big O of n. Now, we know that a constant number here doesn't actually affect the overall time complexity, but that being said, I'm still going to focus on the slightly more optimal solution because it's a little bit more difficult, but it's also interesting, and it's a pattern that's actually used in other LeetCode problems as well. So we're given two strings, S1 and S2, and all we want to do is return true if the string S2 contains a permutation of S1, and we return false used in. And now we know that a constant number here doesn't actually affect the overall time complexity, but that being said, I'm still going to focus on the slightly more optimal solution because it's a little bit more difficult, but it's also interesting, and it's a pattern that's actually used in other LeetCode problems as well. So we're given two strings, S1 and S2, and all we want to do is return true if the string S2 contains a permutation of S1, and we return false if that's not the case. Now, you can get bogged down and really confused with the explanation of this problem, like focusing a ton on permutations, but it means to an O of n. Now, we know that it's n solution, and there's another solution that's actually just big O of n. Now, we know that a constant number here doesn't actually affect the overall time complexity, but that being said, I'm still going to focus on the slightly more optimal solution because it's a little bit more difficult, but it's also interesting, and it's a pattern that's actually used in other LeetCode problems as well. So we're given two strings, S1 and S2, and all we want to do is return true if the string S2 contains a permutation of S1, and we return false if that's not the case. Now, you can get bogged down and really confused with the explanation of this problem, like focusing a ton on permutations, but I'm going to try to simplify this for you immediately without going down too many rabbit holes. And let's actually take a look at this first example. So we see that S1 is the target string. That's what we're trying to look for. We're looking for a permutation of this string somewhere inside of S2. Can we find it? Now, what does permutation mean? Well, we could actually, create a permutation of the string, which would be really complex and annoying. But we see that over here, there actually is a substring of S2, and it's a permutation that matches S1. It's BA, right? The exact same characters, just in a different order, which is perfectly fine. Now, by the way, AB itself technically counts as a permutation of itself. So this string is also allowed. But since you kind of see, what we're really just looking for is there a substring of the exact same size? So this is two characters, so we have to look for a substring of two characters.
Fuck. Permutation, you have to use a hash map. Oh, I did not realize that. It's a permutation if the count of those are equal. Let me try this again. Damn. Oh. I did not realize that. So permutation was the other problem that we did that was like this. Oh, wait, was that anagram? Wait, so what's the difference between a permutation and an anagram? Oh, I see, because it has to be in that order. Wait. Technically, can't they be anagrams, right? Because say you have AB. I feel like technically they would be the same. Like this is a permutation goes one way, but the anagrams are like two ways. It goes both ways, so like. Say we have like say we have like fuck. Okay, that's too many. And we had DC, right? Technically, this has one C, this has one D, and this has one C and one D. Or like, and our string 1 was this. CDE, technically you could rearrange any of these letters and make this. Okay, yeah, I think. Let me just retry this whole thing. Let's just make a hash map of this. So let's use the counter. Let's make a same window, but S2 from left to right +1 if S1 Oh, okay, I got it. But wonder what the time complexity is. Oh, then okay. Okay. I'm not mad about that. Wait, I should have just done it myself. This is Oven. Technically splicing. O of K. So is that technically a constant? So is that basically O of 1? And then this would just be O of N. Okay. I'm gonna see how he did
Here,
it,
right? We
though.
can't just take 3 characters and say that that's the permutation. But, you know, we're looking for a window, same size as this, and it has to contain the exact same characters as S1, just maybe in a different order. Now, does that kind of sound familiar to you? Well, it's the same thing as looking for an anagram, right? We're just looking for the exact same characters. We don't care about what order they're in, right? So it's looking for an anagram. So we can actually use a typical sliding window technique. We're going to look at every window in S2 that's the exact same size as S1. So in this case, length 2. So we're going to look at the first 2 characters, then the next 2 characters, then the next 2, et cetera, until we find an exact match with S1. Now, if we were actually comparing the exact characters, that would be pretty annoying. The time complexity in that case would, let's say, be n times m, where n is the size of S2, m is the size of S1, because we're looking at every single window. But we can do it a little bit better. We can reduce it to be 26 times n if we use a hash map, because actually in this problem, it's written all the way at the bottom of the description, so it's not on screen, but they tell us that all the characters in both of the strings are going to be limited to lowercase a through lowercase z. So therefore, the size for hash map is going to be at most size 26. There's only 26 characters. So as we build that hash map, we're at
N times M.
actually going to have two hash maps. We're going to have one hash map for S1, which is going to stay the exact same. We're also going to have a second hash map for S2, which is going to have the characters of the current window that we're at. So every time we create a window, right, each time we shift our window to the right, we're only just adding one character and maybe removing the character that was on the left. And then once we have those two hash maps, we're going to compare them if they are equal, which is a 26 operation, right? There's only 26 characters. And so that's where we get this time complexity from. But there actually is a better way. This solution is doable. It's easy to code up, and you can do so if you would like, but I'm going to show you the slightly more optimal solution, which is actually not even going to have this 26. It's just going to be big O of n. So let's look at the big O of n solution. And it's actually similar to the previous solution we discussed. We're actually going to still have two hash maps, one for S1. So as you can see, we counted the occurrences of each character. We call it S1 count. So we have 1A, we have 1B, and 1C. So we filled our hash map with the same values. And our S2 hash map is empty because first we're going to set our window here, and then we're going to continue to shift it by one each time. But the difference here is we're not actually going to be comparing the two hash maps together. We won't need to because we're going to keep track of one more variable. We're going to call it matches. We're basically going to have a little shortcut. Initially, this is going to be set to 0. I'll just create a box for it, even though it's just going to be a single value, but we might be updating it to other values. But this matches variable is basically going to be a shortcut that's going to allow us to not have to compare the entire hash maps each time, which we know in the worst case could be a 26 operation, having to look through every single character of the hash maps. Because this matches variable is actually going to maintain the total number of equal characters in each of these hash maps. And actually, even though I didn't draw the entire map for S1 and S2 in this case, because actually we know that there's A through Z, there's 26 characters, and I didn't actually draw out the entire thing, but we are going to fill in the values in the code because we know that the rest of the characters in S1 are going to be of count 0, right? And matches is going to tell us the exact number of matches of each character between the two hash maps. So we want to know, does the A count of S1 and of S2 match? If it does match, then that's a +1. If it doesn't match, then that's not a +1, right? And we want to know the number of matches for every single character, and we want to know that initially, right? It could be 26 matches or it could be 0 matches, right? It could be any value in between. But once we have 26 matches, that means that for some window in S2, and by looking at it, we know that this is going to be the window. We know that this window has 26 matches with this window because they both have a single A character, a single B character, a single C character, and for the other remaining 23 characters, they both have 0 of those characters, so therefore they have 26 matches. That's what we care about, and we can do that with a single variable without having to look through the entire hash map. Let me show you the algorithm to do that. It's pretty straightforward, actually. So first thing we're going to do is actually just look at the first 3 characters of S2 and then fill up our hash map. So we have a single B, we have a single A, and we have a single X. Now you can see that this is what our hash maps actually look like. We have looked at the first 3 characters, and now what we're actually going to do, for the only time, we are actually going to iterate through both of these hash maps comparing each character. We actually do have to do that at least one time, but it's a single 26 operation. So, and then after that, we'll only have to just iterate through this string. So the overall time complexity is going to be n plus 26, which we know is going to be equal to big O of n. It's definitely better than if we were just doing 26 times n. Okay, so we're going to look at every character. A, they both have one A, they both have one B. S1 has a single C, but S2 does not have any Cs. So therefore, they have 2 matches, A and B, but C is not a match. Then we're going to look at all the other characters after C, and we're actually going to see that yes, there is a match, right? Because they both have 0 Ds, they both have 0 Es, they have 0 Fs, etc., etc. But then we're going to get to X. Okay, this has a single X, but S1 does not have any X's. That's not a match, but they both have 0 Ys and 0 Zs. So all in all, they actually matched every single character except for C and except for X. Those were the only characters they didn't match. So actually, initially we have 24 matches. Next, we're going to take our window, which was like this, and we're going to shift it to the right by 1. When we shift it, we're obviously removing a character from the S2 window. We're removing a B. Now, as we make changes to the count, we want to know, does it affect the number of matches? So here we have 1, right, which was equal to what it was supposed to be in S1 as well. But now we're changing it to a 0. So therefore, it's not matching with what it previously was matching with. Therefore, our matches total is actually going to be updated now to be 23. We're decrementing it by 1. Okay, but we also added a character, a Y. Does this affect our matches? Was this a character we were looking for? Well, let's increment our I by 1, and we see that now it's 1, but what was the Y value in S1's count? It was equal to 0, so now we actually created another mismatch. So actually, the total number of matches is going to be 22 now. And now we're going to actually shift one more time, so this A is no longer going to be in our window. Now we're going to have XYZ in our window. So we remove the A count is now going to be set to 0. We created another mismatch, so our matches count is now going to be 21, but we added a Z, so our Z count is 1, but the Z count in S1 is 0. Therefore, we created another mismatch, so now our total number of matches is actually going to be 20. Now let's shift our window one more time. Let's chop off this X. So X count is now going to be set to 0, so let's update that. X count is now set to 0, which is good for us because S1's X count was also 0, so therefore we can actually increment our number of matches now, right? So let's set matches now equal to 21. We also added a character. We added this A character at the top, so let's actually increment the number of A's. We went from having 0 A's to now having 1 A, and that's what we were looking for, right? Because 1 A is also found in S1 count. So now we can increment our number of matches from 21 to be 22. We're getting closer to our goal. And I'm going to kind of fast forward the remaining 2 spots. Clearly, we're going to see that the Y gets chopped off, and then we're going to add the B character, which is also what we wanted to do, right? We have 1 B and we have 0 Ys. So that brings us to be 24 matches, and then we're going to shift one more time to be at this last window. We're going to get rid of the Z that we didn't really need. So now our number of Z's is 0. That's good. That's exactly what we want. And we added a C character. So now we have 1 C. Now we have the exact number of matches we were looking for. Our matches count is going to be 26. Whenever we get to 26 matches, that's our magic number. We are going to go ahead and stop the algorithm and return true, because all we're looking for is, does there exist a single permutation of this in S2? Or in other words, does there exist an anagram of S1? And there does. We found it. We return true immediately, and we can stop the algorithm. That's the big O of end time algorithm. Now let's actually code it up. Okay, now let's write the code, but there's just one little edge case we actually have to look for that I didn't talk about previously, and that's if our S1 string is actually shorter, or actually rather longer than our S2 string, which would make it impossible for us to find a permutation of S1 in S2. In that case, we can just return false immediately. But after that, we can get into our standard algorithm. Even though I was talking about hash maps, we can actually implement these with arrays as well, because we are getting fixed values, lowercase a through lowercase z, and we can convert those characters to be integers, and we can use those integers as indexes of our 2 arrays. So initially, I'm just going to set these to be 26 numbers, and each of those numbers is just going to be a 0 for now. We're going to go through every character in S1, and we're going to go, so suppose S1 is maybe 3 characters long. At the same time as we're going through S1, we're also going to go through the first, let's say, 3 characters of S2. So we're going to initialize both of these hash maps at the same time. So let's do that now. So the way we're going to convert these characters, so in S1, we're going to get the character at the ith index, and we're going to use the ORD function. Now, depending on your language, it might be a different function. All we're doing is getting the ASCII value of this character with our ORD function, and we're going to subtract from it the ASCII value of lowercase a. Let's get this right. And this will map to an index. This will map to one of the 26 indexes. And to this, all we want to do is just add 1 to it. And I'm just going to go ahead and copy and paste this line and do the exact same thing for S2. We're going to, in S2 count, we're going to update the count of this character and just increment it by 1. So now before we actually get to our sliding window portion, don't forget we actually have to initialize the number of matches. We're initially going to set it to 0, but let's compare each of these maps or arrays. We know that there's going to be 26 spots in the array, so we can actually just hard code that. So now we're going to say, to the number of matches, we want to add 1 to it only if S1 count at index I is equal to initialize the number of matches. We're initially going to set it to 0, but let's compare each of these maps or arrays. We know that there's going to be 26 spots in the array, so we can actually just hard code that. So now we're going to say, to the number of matches, we want to add 1 to it only if S1 count at index I is equal to S2 count at index I. That's the only case where we'd want to increment this by 1, but if that's not the case, then we are not going to increment it by 1, so we can just say else 0, right? So else increment it by 0, which is the same as not incrementing it at all. Let's put parentheses here just to clean it up. And now we can move on. So now we're going to do the sliding window portion. We're going to initialize a left pointer to be at the beginning, so at index 0. So then we're going to have our right pointer, which is actually going to iterate through every position in S2, but we know we don't actually have to start at the first position because we already initialized our windows. So we're actually going to start at the length of 1, the length of S1, because this will start us at the next character that we left off at, right? And this range is actually non-inclusive, so we stopped before we reached this index, so now we're actually going to go to that index with our right pointer. But remember, what happens if matches is 26? Shouldn't we return immediately? Yeah, we can put a return statement outside of this for loop, but it'll be redundant, so we can actually put it as the first statement inside of the for loop. So basically, if matches is equal to 26, then we are returning true. If that ever happens, we can immediately return true, no questions asked. But if it's not the case, then we have to update the number of matches. We know that we just visited a character at index R, and this is the part where you actually might have hoped that you would used a hash map rather than an array, and that's fine. If you want to rewrite the code that I'm about to write using hash maps, I think it's perfectly fine, but I feel like I usually overuse hash maps, so this time I actually wanted to kind of show you guys the array solution, even though it's a little bit more annoying, because remember, our character is not the key of our array. We have to map that character to an index, and we can do that just like this. So S2 at index R minus ord of lowercase a. So we're also going to take the ord of this because that's how we're getting the index of our count arrays. So now we can actually use this index, but what are we going to use it for? Well, we know that
For R and okay, so that's the right pointer.
this character is the character that was just added to our window in our S2 use this index. But what are we going to use it for? Well, we know that this character is the character that was just added to our window in our S2 string. So we're going to increment the count of this by 1. But now that we just incremented the count of it by 1, it could be 1. But our S2 string. So we're going to increment the count of this by 1. But now that we just incremented the count of it by 1, it could be possible that now it exactly equals the count in S1. So if that's the case, if now that we incremented this and now it finally equals exactly S1 count at the same index, at the same character, then we can increment our number of matches by 1. But it's possible that also by incrementing this, instead of making it it's possible that also matches by character, then exactly equal, we made 1. That's how you know we, instead of making it exactly equal, we made it too large. We made it exactly bigger than the target by 1. Also of matching index at this in could be 1. But now that we just incremented the count of it by 1, it could be possible that now it exactly equals the count in S1. So if that's the case, if now that we incremented this, and now it finally equals exactly S1 count at the same index at the same character, then it exactly equals the count in S1. So if that's the case, if now that we incremented this and now it finally equals exactly S1 count at the same index, at the same character, then we can increment our number of matches by 1. But it's possible that also by incrementing this, instead of making it exactly equal, we made it too large. We made it exactly bigger than the target by 1. That's how you know we have got to actually decrement the number of matches. So basically, else if S1 count at the same index plus 1 is now exactly equal to S2 count at the index. And if this is the case, that means they were equal, they were exactly equal, but we just incremented S2 count by 1, so now we made them unequal. So then we actually have to decrement the number of matches by 1. Okay, and that's pretty much the entire algorithm, but there's one last thing, and I'm just going to go ahead and actually copy and paste this entire block. Because we're going to do the exact opposite thing. We know that we're adding a character to the right of our window, but at index L, at index left, we removed a character. So we're just going to replace this with the opposite case. Right here, I replaced the R with an L. And here, instead of incrementing the count, we're going to decrement the count because this is the character that we just removed from the left side of our window. And here, what we're going to say.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem permutation in a string. And there's actually two solutions to this problem. One is the 26 times n solution, and there's another solution that's actually just big O of n. Now we know that a constant number here doesn't actually affect the overall time complexity, but that being said, I'm still going to focus on the slightly more optimal solution. Because it's a little bit more difficult, but it's also interesting, and it's a pattern that's actually used in other LeetCode problems as well. So we're given two strings, S1 and S2, and all we want to do is return true if the string S2 contains a permutation of S1, and we return false if that's not the case. Now, you can get bogged down and really confused with the explanation of this problem, like focusing a ton on permutations, but I'm going to try to simplify by incrementing 6 numbers is just going to be a 0 for now. We're going to go through context. This will map to one of the 20. Move on. So now we're going to do the sliding window portion. We're going to initialize a left pointer to be at the beginning, increment it by 1. So we can just say else 0, right? So else increment it by 0, which is the same as not incrementing it at all. Let's put parentheses here just to clean it up. And now we can move on. So now we're going to do
the sliding window portion, we're going to initialize a left pointer to
That's
be
what
at
I
the
did
beginning, so
here.
at index 0. So then we're going to have our right pointer, which is actually going to iterate through every position in S2. But we know we don't actually have to start at the first position because we already initialized our windows. So we're actually going to start at position because S2 initial 1x loose x with turn visited that you used a hash map. I wanted to kind of show you guys the array solution, even though it's a little bit more annoying because remember our character is not the key of our array. We have to map at index of this character exactly equals incremented out 4. Well, we know that this character is the character that was just added to our window in our S2 string. So a character that was just at the count of 1 count is same character, but its pop can increment also by incrementing this in exactly bigger than the target decrement count at the index. Index plus 1 is now exactly equal to S2. Well, now we by 1 to copy and that's so then we actually have to decrement them, but there's one because we're going to do the exact copy and paste thing. X left right here and this but exactly somehow by now being 2 minus 1, if we changed it from being exactly equal to now being slightly too small, that's when 1. If we changed it from being exactly equal to now being slightly too small, that's when we are going to do this block increment in each. Instead, we're going to make sure that it works. It's going to return flashes equal.
Maybe we can try the hash map implementation of this. I don't really get this, to be honest. So we have matches. For I in range 26, how would I do that with a hash map? For key and for key value in oh, I see, yeah. Alright, give me a sec.
Huh?
Give me a sec.
How long?
10 minutes. Alright, I have to go in like 10 minutes. So, probably just finish this problem. And, I'll upload like a part two of like me doing the other coding stuff. Cause every time I try to like splice together two videos, then it always becomes like too large. Like I think I had two parts recorded and they were each uh 3 GB, and then I combined them together in iMovie, and then it became like 24 GB, and I was like damn. Um, so you splice it into length of S1. So you iterate through it. Man, this code is hella long. I don't even think I'm doing it right. Okay, low key.
Cool, 20. It's pretty. Now let's run the code.
Oh, default dict. Oh, I see. Okay, never mind. I think this is the hardest one I've done so far. Last one was a lot easier than this, to be honest. So so we initialize these hash maps. Mm. So you do for I in range length S1, and you initialize the counts, and then match equals 0 for char in S1. What is S1 count? That's a hash map, right? So is that like the key? I guess so. And it would increase matches by 1. Set left equal to 0. And then if you do if matches equals the length of S1 count, then huh? Give me a sec. So if you have R in range length S1, S2, if matches equals length S1 count. If matches equals, oh, I see. So if every one of these are, if these are true, then also if the matches are, so if the number of matches equals the length, oh, okay, that makes sense, of the first string, then you know it's a permutation. Otherwise, this solution low-key confusing, can't lie. I think that 26 times n is fine. That is a lot easier, to be honest. Char equals S2 at R. So you increase it by 1, and then if so if the count is equal to S1 count at char, then you increase the matches by 1.
You wanna come and eat?
Yeah, in a sec.
How long?
I don't know, I'm almost done.
Alright, just come down when you're done then.
So you increase the matches by 1. Okay, if they're equal, you increase, but there's a possibility that you just unmatched one. So if count this new char, so if it's equal to that count by 1, then we just mismatched it. Okay. Uh-oh. Char equals S2 at left. Now we do the same thing for the left, so oh shit. Fuck. Minus equals I. Okay, so we just reverse it. We have to increment left by 1, and then return. And this, is this within the for loop? Oh, this is like the end. What'd I do? Let's see. Wait. I didn't even get all the code. No, so this doesn't work. Loki, I think someone probably has it in the solution here. So this is what I did. For Iron Range, those two, if it's encounter. Huh? Is this not these lines not the same? But they did minus equals and plus equals, so what's the point? Okay, I'm just gonna go with my own solution for now. I get Nicode's solution, so that's good, but it's a little hectic and confusing to code out. Let's see. Okay. Okay. For the left index, subtract it out. If the new index is equal to, then we match it. Otherwise, okay, yeah, this makes sense. I have to go, so I'll upload part 2 later when I do it, but I'll see you until then.